Hello dear all. Welcome to the second course of switching parasitics and how to deal with them. As you remember, in the last course we have investigated a synchronous DC-DC converter which has two actually switching MOSFETs and an LC filter. We were discussing about the parasitic oscillations and how to deal with them. So we had discussed about the gate driver design. Today we are going to focus on the further steps to overcome these oscillation problems. Just for you to remember it, when we put an parasitic inductance, which is actually called as power loop inductance, on the switching path, the instantaneous voltage also emerges on the drain to source terminals of the switching components during switching transients. In order to handle this problem, because these MOSFETs are actually rated to 100 volts as maximum, so as you can see now the voltage goes beyond 140 volts, we need to reduce this peak volume. Moreover, we need to overcome these oscillations in order to inhibit any EMI problems. We need to take some action. So we had discussed, as I just said before, we had discussed about the slowing down the gate driver speed. We had talked about the design criteria of the gate drivers, and then we discussed how to slow down the gate driver speed. So you can see the gate driver circuit we had talked about in the last course here. So today we are going to talk about the Snubber circuits. Then we are going to discuss the eliminating high inductances. So let's begin with the Snubber circuits. Okay, mainly the Snubber circuits are used to eliminate the high voltage overshoots, to reduce the transient speeds and suppress the EMI noises. Note that we are actually reaching the elimination of high voltage or suppressing the EMI noises by reducing the transient speeds. Actually, that is the cause and these are the results. However, we need to pay some for reach these criteria that we want actually. First of all, we have to increase the switching losses. As you can predict easily, the switching speed and the switching losses are directly related, because let's draw some curve. Whenever our, let's say, the voltage reduces and at the same time our current increases, let's write it I switching and V switching. So the duration of this, let's call this as T fall with respect to the voltage if we give a name. So actually we are increasing this period, the fall time, so it increases our switching losses as well. Moreover, we need to put some additional components to have a snubber which is connected to our circuit. The additional components, and we are observing actually some additional losses on the snubber components which are considerably high, as high as a loss on the switching loss actually. So we are going to now focus on these details. So let's begin with a C snubber. Let me show the how we connect them. Here is the drain top, which is called actually such as it is top switch, and this one is low switch. So the drain top is the drain pin of the high side switch, and we have the switching node here. It is called as the switching node. We give a name as source top for this case, and the source bottom or the ground are the same nets. So we are actually connecting two capacitances in parallel with these MOSFETs. What it means actually, that let me draw it in more detail. If we say that this is an ideal MOSFET model, let's let it to be an N-channel MOSFET. Actually, it does have some parasitic capacitances across the drain to source terminals, drain to okay, drain to gate terminal, and moreover gate to source terminal, and these are effective during the switching transients. So what we are doing here is actually connecting a new capacitance across the drain to source to slow down the transition speed, because these capacitances, the total capacitance which is in parallel with drain to source terminals, has to be either charged or discharged during the switching transients, and if we increase the capacitance here, it slows down our circuit. Let's see the waveforms of this solution. Here you can see that let's talk about what we had increased here. The first case, okay, let me cancel out my personal view. In the first case, we are not using any snubber, external snubber, In the second case, we had connected a snubber capacitor, which has the capacitance equals to 1 COSS. And in the third case, we are actually using 5 times of COSS at the output port, and in the last case, we are using 10 times of parasitic capacitance connected across the drain to source pins. Here, when we check the drain to source voltage levels, the overshoot levels, it was as high as 160 volts in the first one. However, it reduces down to 100 and almost 20, let's say. So we are actually decreasing the voltage as 40 volts from the first case to the last case. However, it comes with an increased oscillation which starts during the switching moments. So actually, it doesn't solve our problem. Okay, it solves our problem in terms of reducing the over voltage breakdown stress. However, it causes very large amount of oscillations on both the voltage and the current. So it causes very strong EMI radiations on our circuit board. So we never want to have such an oscillative voltage or the current waveforms. Therefore, we need to solve this oscillation problem. But first, let's check about the switching losses of these different cases. As you can see, since the voltage level decreases, the switching losses decrease as well. However, it's again, as I said just before, it causes very large amount of oscillations, so it is not useful. Okay, another thing that we can do is actually to connect in series with these snubber capacitances. We can connect an external resistance in series with these snubber capacitances. Note that resistor is actually known as an oscillation killer or damper because it dissipates the oscillating power between the power loop inductance and the snubber capacitances. So we need to see that the oscillation waveforms should be eliminated for a resistive situation. Okay, here are the waveforms of this case. Okay, now for all of the case, the snubber capacitance is equals to actually the 10 times of our output capacitance. However, what changes from first case to the last case is the snubber resistance. As you can see in the first case where the 0 ohm resistor is used or a resistor is not used, we see very large amount of oscillations. However, when we check the last case, which is the 10 ohm case, we are only observing the overshoot but not the oscillation, which is a good news for our design. Okay, based on the results, let's think about which one is the best one. Okay, maybe it is better for me to place me to the upside to see the loss ratings. Okay, the blue one is the loss on the high side switch. The black one is on the loss on the low side switch, And now the red one is the loss on our snubber resistance. Let's write it here, our snub, this one. Okay, that is the low side switch and that is the high side switch. So we can see that even though the eliminating the oscillations decreases the switching losses considerably, it causes another loss on the snubber resistance as well, and it increases with the increased snubber resistance, as you can see on the bottom side. So based on the waveforms and the results, we can say that the option with 5 ohm is actually the most suitable one, since the oscillation is almost eliminated, and moreover the switching losses are lower than the 10 ohm case. So we are going to talk about this case in the further slides. Okay, for this purpose I had analyzed, I had searched for some resistor options to be used in the circuit. As you can see, all of them has the 5 ohm rating. Okay, let me put here. And these resistors are capable of operating at 2 watt continuous loss. So I had analyzed the space now. The MOSFET, the power MOSFET that we are using in this circuit has these dimensions. However, the snubber resistor, which has these ratings, has a dimensions which is larger than our MOSFET. So the total area of our snubber resistor is actually 2.7 times more area than our MOSFET, which means actually that in order to reduce the overvoltage, the voltage induced on our switching components, and in order to eliminate the inductances, we need to pay this price with the increased space limitations for our circuit. So that is the drawback of this design. Okay, that actually explains many things if we consider a converter design in general, because converter design is a kind of study that we try to optimize a converter in terms of some parameters such as the sizing, efficiency, circuit noises, the reliability issues. I mean, it should be operating with fault situations, or it should be a fault tolerant circuit. Moreover, the controlling capability is very important for which depends on the application type. The cost is also important, and the generalizability, which means that we need to use a converter in different kind of purposes, with different kind of purposes in different type of applications. Actually, I believe that the optimization of any 4 of these criteria can be a subject of a graduate study or a thesis work for the master program. So here we changed the Snubber design with the R parallel D connected in series with the capacitance. So maybe just to clarify it, let's draw our MOSFETs, the switching components here. That is our one MOSFET, the high side one. Okay, and that is our low side MOSFET. So these snubber circuits are actually connected, such as this one. Okay, now we have put a diode in parallel with this snubber resistance to decrease the losses, and moreover to eliminate the high oscillations. Note that these diodes should be able to carry our DC link voltage. They should be operating with this DC link voltage, but the currents are very minimal. So here we are comparing the high side switch losses, again the low side switch losses, and moreover the snubber losses, which includes both the diode and the resistive losses. As you can see now, actually the loss on the snubber components decreased significantly. However, the loss on our switching components increased very little, so we can continue with this RDC, R parallel D type snubber circuit to overcome our oscillations further, or the reducing our maximum voltage level, and it can be shown here as well. The voltage is reduced for the peak value. So another snubber which is commonly used for a flyback converter is given here. Here now we see that the resistor is in parallel with the capacitance, and they are connected in series with the diode. However, this converter will be investigated in the next semester. So now I am just showing this for you to remember for your further studies. So here we actually need to understand something important. Some topologies include the transformer, and some topologies does not include. So if there is a transformer on this converter, it should have some leakage inductance, which actually acts as a power loop inductance. So the leakage inductance can be minimized by optimizing the winding topology of this transformer. However, most of the time it is not that easy to minimize these leakage inductances of the transformer. So most of the time you need to use an external snubber circuit for a topology with a transformer. However, for the circuits that we were working in the previous case, which was a synchronous converter, let me draw it once more here. Okay, there was an inductance, a capacitance. Okay, we have maybe it is better now. We have a current sink, it is the load, and the input voltage. So here actually the inductance is mainly caused by our PCB design, and the in-package inductances of our MOSFETs or the other type of switching components. We can do something to reduce these PCB inductances by optimizing our layout design, and we are going to talk about them in the next slides. So in terms of the Snubber design, I want you to search for search on the internet to find different type of sources for helping you about these designs. And I also recommend you to always simulate the circuit before the implementation. There are some analytical solutions on the application notes on the internet. However, I recommend you still to check for a simulation before implementation and get prepared to have a change on the Snubber components, and please make a PCB design by considering this fact, actually the being prepared situation. Moreover, please do not forget that the Snubber circuits are also not ideal, and they have a frequency dependent impedance as well, because we are now using the capacitive or the diode type components, which both have some parasitic values. For example, the capacitance has a leakage resistance, or it has a ESR value which is in series, or a diode has a capacitive value as well. So please remember that we are now trying to solve a high frequency oscillation by using these snubbers. So their impedance, the frequency dependent impedance, is critical as well. And you need to connect the snubber components as close as possible to your switching circuit. So let's say we have a MOSFET like this one, and we are using an RC connection, an RC snubber. Okay, we have a R and a capacitor across the drain and source pins. So if you do not put this snubber as close as possible to the MOSFET, it causes some induction some inductor on the layout, and this means that this snubber will not work effectively against the oscillations or the high frequency switchings. So you should always place these snubber components as close as possible to the switching components. Okay, up to now we have investigated the gate driver design, the snubber circuits, and the next step is eliminating the high inductances. Actually, if we use a snubber for a PCB without a transformer, it means that we actually had designed our circuit very bad, and we now need to reduce the driving speed of this PCB, which increases the switching losses and the required spacing on our board. So in order to eliminate this kind of problems, we just need to optimize our layout design. So let's continue with this issue. Okay, first of all, I would like to ask you that please consider we have a printed circuit board which is given on the bottom side as well, and we have a wire on the left hand side. That's a wire which helps us to connect the bottom layer to the top layer, and another wire is here. And let's think that we have a current source which is connected here, and it supplies some AC and plus DC current to this copper track. Okay, it is actually shown on the top side figure as well, and the schematic is given on the right hand side. And the question is that how should we design the bottom layer, the returning path for this current, to minimize the resistance and the inductance? Actually, that gives the answer for our layout design for switching circuits as well. So let's begin with the DC current path. Okay, we are now ignoring the AC component, and let's say we have only a DC component. And we know that the inductors act as a short circuit for a DC operation. So we here do not need to think about the inductors, but we need to focus on the resistors. We know that the current should follow this path on the top layer because this is the part that we have a copper, but for the bottom part we need to draw our layout, and let's think about different type of layout designs. Let's say I had put some path such as this one for returning current on the bottom layer, and I had put another parallel layout trace such as this one. Okay, where the DC current does flow? The answer is that the DC current should flow in both one. However, since this one has lower resistance, let's call it as R1, and let's call this one as R2. Since R1 is lower than R2, the current going on the I1, the R1 should be higher than the I2. So it means that actually the DC current always prefer to flow through the minimum resistance path. So what should be the result for a plane? Let's consider about that. Okay, for that purpose, let me clean these ones. Okay, now where it is? Okay, the pen. Okay, let's say we have plotted a large copper region on the bottom side, and both wires are connected to this copper field, the copper region. Okay, that's a copper region. So the current can pass through anywhere on this copper region. However, the DC current should follow the minimum resistance path, so it accumulates around this line. However, it also still passes through the outer lines with reduced current density. So that should be our current distribution for a DC conduction path. So let's think about now the AC current path and just ignore that the copper does not have any resistance. So the thing is that the AC current should follow the minimum inductance path. So the rule of thumb is that the DC current should follow the minimum resistance path and the AC current should follow the minimum inductance path. So the question is that where should we put our conductor to reach out minimized inductance volume? Okay, it totally depends on our flux linkage. As we all know, the inductance is actually defined as the flux linkage over current. So the question is that how can we minimize the linked flux for this returning current path? Okay, if I put a current flow path such as this one, now the current comes through the top layer with this trace and returns back on the bottom layer with this trace. Now we are actually accumulating all the flux across this region. However, we want to minimize this, and you can see that we can obtain a minimized solution by just let's say we have a path such as this one. Okay, let me clean these small lines. Okay, let's say I had put a path such as this one. Now the flux will be linked only this region, so my inductance will be lower. The most optimum case, let's draw that one as well. The most optimum case is that for PCB to reach out minimized inductance, the path should be put just below the top trace. Okay, what I need is to plot a bottom layer copper just at the under of this top layer. So what happens is like that. Let me draw the current flow with red color on the top layer. It flows like this. It goes like that. Okay, this is only a AC current as we talked. And on the bottom layer, now let me draw the bottom layer current. It flows back on the opposite direction, and that is how we reach the minimized inductance, because now we are coupling the minimum flux linkage on our board. Okay, so that is how we reach the minimized inductance for our AC currents. And as I just explained, the region that the coil has actually gives our the inductance as well. So we need to minimize this region always, and for that purpose we need to place the pads on top of each other on different layers. And that's then another view of this concept. Let's say we have an AC current which flows from plus to the minus. If it follows a path such as this one, it will couples all the flux inside this region. However, if we put a layer on the top and if we place another layer on just at the bottom side of this top layer, it follows the minimized area, so it couples less flux linkage, so the inductance is reduced. Okay, for the actual answer for this with an AC current should be like that, because we know that the copper has also some resistance, so it optimizes the inductance and the resistance, and it follows a path which is drawn on the bottom side with these arrows. So that is the most optimum path for a current to flow if we consider the resistance and the inductance as well. So let's discuss about our switching current. So let's say it is our MOSFET current, and it turns off. Okay, that is the I MOSFET. Now it has a steady state value, and it is very similar to the DC pad, so it should follow the minimum resistance pad, and we need to place the minimum resistance pad to the returning layer of the returning path of the layer. However, for the switching situation, we see here a very strong d over dt. Actually, it means that we have an AC current for that purpose, and the AC characteristic is really dominant to the DC characteristic. So we also need to place a layout such that the minimum inductance is available for the switching transients, and the minimum resistance is available for the steady state moments. If we don't have the inductance, if we don't have the minimum inductance path for this circuit, it means that the power loop inductance will be increased. A loop, let's write, will be increased if we don't place the minimum inductance path. However, if we don't place the minimum resistance path, the resistance of our loop, let's say, will increase, and it is going to dissipate some power on our printed circuit board, and which will heat up both the printed circuit board and our components as well. Okay, let's now talk about the switching loop design for the power loop. We will be discussing about a circuit which was like that. We had a power loop inductance as 100 nanohenry, which is connected with our DC source, such as like this one. What can we do to reduce this inductance is that we need to place some power loop bypass capacitors. Most of the time they are the ceramic capacitors, because their frequency response is quite good. We can actually now reduce this the inductance. Actually, we can leave the inductance outside of the power loop, because now the power loop is defined as this loop, and any current comes with a very high frequency, let's say. We know that the impedance depends on the frequency as proportional, and for the capacitance it is inversely proportional. So if this current, such as a switching current, has a high frequency component, this path, the inductive path, should have much higher impedance than the capacitive path. So this current is going to flow through our power loop capacitor to circulate around the power loop. However, if we do not put this power loop capacitor here, this current, nothing there can do, should flow this path, and we'll see very large amount of inductance. So we need to use the power loop capacitors as closely connected to our switching components. And the layout design is quite important here, and we are going to discuss them in a couple of slides. So let's talk about the gate loop as well. So let's say we are using the similar turn on and turn off resistance, and we have a BJT circuit, let's say. Okay, that's a BJT, and we have another circuit such as this one. Okay, as we all know, it is supplied with a power supply. Okay, now when we actually want to, let's connect this one to here, when we want to turn on our MOSFET, we need to charge the CGS across the gate to source pin. So we need to supply a high frequency current on this loop. However, as you can see now, the current is supplied by this power supply, and it sees some inductance on the path and returns back with a large inductive path. So what we need to do is again to connect a high frequency gate loop capacitor to supply this current. For that purpose, we need to connect a capacitance from the power pin to the ground pin to supply the high frequency current for the gate driver purpose. That is the path it follows. So usage of capacitances really important for reducing the oscillations and optimizing the layout inductances as well. More importantly, as we had discussed before, the placement of these capacitors also important. The gate current, okay, now it is drawn here as a pulse source, but we all know that this is actually a capacitance. So we need to connect this capacitance to the gate and the source pins such as it doesn't couple with large amount of flux while the current returning back to the capacitor. For that purpose, we need to put the return current path just under the coming gate current path on the top layer or the other layers. So this is valid for the power loop as well. Okay, we should not connect our capacitor significantly away from the switching component because it increases this inductance. We need to connect this capacitance as close as possible such that the current flows back by following the path just beneath the top layer current path. So in order to increase the tolerance of our layout for DC and AC currents, most of the time we are using the power planes, which are the copper regions lays on our printed circuit board. These are the important tricks to minimize the resistances and the inductances for our critical layout design. So as I just explained before, usage of capacitors effective is very important concept because these capacitances are not ideal. I mean, for a high frequency application, we cannot use an aluminum electrolytic capacitor because it has a very large amount of parasitic inductance volume. Most of the time, we prefer the ceramic capacitors because of their wider bandwidth. However, the selection of capacitance depends on many parameters such as the capacitance density, the temperature sensitivity, because the capacitance of the capacitor changes with the temperature, the current handling capability, or post-failure situation. For example, an aluminum electrolytic capacitor becomes a short circuit after a failure. However, a tantal capacitor can be used even after the failure situation. However, the aluminum electrolytic capacitor has the most dense capacitance, so you can reach out to high capacitance values with small footprint areas. Moreover, for a product, the lifetime is also very important for the selection of capacitors, and these are the parameters that you need to focus while designing your converters. Okay, here we actually pictured a sensitive IC which actually needs a sudden current demand. So who is going to supply this current? In this situation, this current should be supplied with these long cables. As you can predict, it causes very significant amount of inductance for all paths. I mean the incoming path and the outgoing path. So actually the sudden current demands cannot be replied by the supply due to these inductances. In order to solve this problem, we always need to place a high frequency capacitor close to our IC circuits, and we need to place the low frequency capacitors across the input terminals of our PCB. Okay, in order to just to classify, this is an aluminum electrolytic capacitor, and this one is a ceramic capacitor, which are used for different purposes. That's an example I had found. I had found this one on the internet. As you can see, this IC is supplied by these capacitances. These are the ceramic ones, and it is also connected to these aluminum capacitors. It is also valid for the below the bottom part of this printed circuit board. As you can see, even for the ceramic capacitor, the smaller one has the higher bandwidth, so it is the most closest one to our IC, and the larger ceramic capacitors are connected just next to the smallest one, as shown on this figure. Placement of capacitors are very important to handle, to overcome many problems that you can see during the operation. Okay. Another thing that we need to pay some attention during our design, that we need to separate the ground signals for our analog signals, digital signals, or the power signals. An example is given here. For example, this in this region, let me draw the boundary part of this region. Actually, here the analog signal operates, and on the right hand side the digital signal operates. As you can see, the ground levels are actually the same. However, these are connected to each other. Let me draw it to each other with a very tiny amount of copper. It is important to hold the analog currents inside this region, and it is important to have all the digital currents inside this region, and if we mix them each other, it will distort our analog signal and the digital circuit as well. So our power circuits are actually the analog circuits with some strong currents or the voltages, and we need to separate them from each other. We can use a tiny connection between them in order to minimize our noise stress. So this is the last slide of our design. In these two courses, we had investigated the design of a gate driver. We also checked for a Snubber design to eliminate the oscillations and to reduce the voltage stress. But the most suitable, the most impactful designs should have optimized their layouts to eliminate any requirement of a snubber circuit or slowing down the gate driver speed. Okay, thank you for your interest and watching.